Okay, so this lecture we look at the stability of amplifiers. Like the last lecture, you may have seen much of the stuff before in your undergraduate courses. So this is partly revision, partly hopefully there will be some new insights. So let's begin with the negative feedback loop and the closed loop transfer function being A over 1 plus A beta. So ACL is a closed loop gain and A is the open loop gain. And you know that the feedback factor varies between 0 and 1. 0 indicates, of course, no feedback, an open loop system, and 1 implies a unity gain feedback. Beta is never greater than 1 because for high gain amplifiers, 1 over beta is a closed loop gain, and you want the closed loop gain to be at least 1. You don't want it to be less than 1. So beta has to be always less than 1 so that 1 over beta is greater than or equal to 1. From a perspective of frequency response and stability, beta equal to 1 corresponds to the worst case condition, and so we will consider the case of beta equal to 1, and whatever we uh, conclude will be valid for beta less than 1 also. Alright. So let us ask the first question that is asked in discussing stabilities. With beta equal to 1, what happens if at some frequency omega 0, A of j omega 0 becomes equal to minus 1? Or in other words, the magnitude of of j omega 0 is 1 when the phase of a j omega 0 is minus 180 degrees. Right, this is the question to begin our discussion. And okay, I'm sorry, there should be a pause here, so you please pause and answer this question. What happens when if aj omega 0 becomes minus 1 at some frequency omega 0? What happens to this amplifier? So we've connected an amplifier in a negative feedback loop. You made it a unity gain feedback, and it so happens that the transfer function, the open loop transfer function, is such that at some frequency omega 0, aj omega 0 is minus 1. Alright, so what will be the output if you were to watch the output on the oscilloscope of this system in the lab? What will you see and why? Alright, so you please pause and think and perhaps write down what you think would happen. Here, pause. Alright, let us think about it. So before we begin our discussion, let us define the term phase margin. Alright, phase margin of a transfer function A. By the way, I am using consistently as an open loop gain. The phase margin of a gain A is defined as 180 degrees plus phi 0, where phi 0 is defined as the phase of the gain A at some frequency omega 0 minus the phase of A at low frequencies. Alright, mid-band meaning, or mid-band is a more general term. For us it will be low frequencies where A is basically independent of omega. It will be a flat line in the Bode plot. So that phase. Usually this phase at mid-band is 0 or 180 degrees, right? Either the gain is positive or negative. If the gain is positive, this phi is 0. If this is negative, this phi is 180 degrees. For this lecture, for simplicity, we'll assume it to be 0, right? So that this term doesn't appear and we are left with only 1. What is A omega 0? A j omega 0 is the gain. Omega 0 is a frequency at which the gain becomes 1. Alright, so what is phi 0? With this phi equal to 0, phi 0 is the phase of A at the frequency at which the gain becomes 1. And 180 degrees plus this phi 0 is called the phase margin. Typically phi 0 is, well, yeah, typically almost always, not always, but almost always phi 0 is negative, and it is can be anywhere between 0 degrees and minus 360 degrees, or even more negative. All right. Okay, actually, now let me go back then. Let us, I think I'm not going to answer this question for some time. So let us answer this question. What happens when a j omega 0 is minus 1? All right. The answer is that, first of all, in this equation, the denominator becomes equal to 0. If the denominator becomes equal to 0, what it implies is that in this system there can be a finite output with a 0 input, because VO is equal to A over 1 plus A beta into Vs. 1 plus A beta has become 0, so even if Vs is 0, then even then VO can be a finite value. That is one way of putting it. What are the circuit implications or the actual signal implications of this? That an output can exist without an input in this circuit. What is the nature of the output? Can this be any output, or does it have to be a specific type of output? The answer is an output can exist only at the frequency at which A, well, beta is 1, so A has become minus 1. And that happens only at one frequency, omega 0. Therefore, the output can exist for a 0 input only at the frequency omega 0, at which A j omega 0 is minus 1. Alright. So the output is going to be a periodic function of frequency omega 0. That is the second conclusion. What is the third question to ask is, what is the shape of this periodic function? Is it sine? Is it square? Is it triangle? What is it? So we get a periodic output, but what will be the shape or the nature of that periodic signal? The answer is it will be sinusoidal, not square, not triangle, sinusoidal. Why sinusoidal? Because the very derivation of this A, either the closed loop or the open loop, in terms of omega is done with the underlying mathematics that omega corresponds to a sinusoidal signal. This is the A j omega, the open loop transfer function or the gain, is derived as a Fourier transform of the original time dependent differential equation, and Fourier transforms correspond to sinusoidal signals. So these omega in all these equations in all of electric circuits refer to sinusoidal signals. Therefore, when we say that A j omega 0 is minus 1, what we are saying is at a sinusoidal frequency of omega 0, A has become minus 1. And at that frequency, an output can exist without an input, and therefore it is a sinusoidal signal that one sees at the output. And that, of course, is instability, right? If this condition is satisfied, then we say that this amplifier is unstable under negative feedback or feedback conditions, because without an input it gives an output. In amplifiers we don't want to see an output if we don't not applied an input. We want the output to be some multiplier of the input. We don't want any output if there is no input. Then that is why this is unstable. Alright, let's go ahead. So let us study the phase, and so we're going to relate instability or this phase of minus 180 degrees to the phase margin and the phase of the gain or the transfer function. So let us study phases of transfer functions with 1, 2 and 3 poles, and then we'll come back to the As we do this, we'll discuss stability. So let's think of a single pole transfer function a0 over 1 plus j omega by omega naught. And let us think about the phase of A. Alright, and this is just the Bode phase plot that we are tabulating here. So we say that for omega much less than omega 0, this term can be neglected, and so A is equal to simply A0, and the phase of A0 is 0 degrees. So for frequencies much less than omega 0, the phase is 0 degrees. When omega is equal to omega 0, then this is 1, so we get 1 plus j. The phase of 1 plus j is tan inverse minus 1, or in the denominator tan inverse 1, in the numerator minus of tan inverse of 1. Tan inverse of 1 is 45 degrees, so we get a phase of minus 45 degrees. For omega much greater than omega 0, we can ignore the 1, and so the approximate A is A0 omega 0 by j omega. The j gives a phase of 1 over j gives a phase of minus 90 degrees. Alright, so this you know, so this is a revision. So in the Bode phase plot, the phase is 0 at frequencies much less than the pole frequency, minus 45 degrees at the pole frequency, minus 90 degrees at frequencies much greater than omega 0. So these are approximate numbers. So for omega equal to 0.1 omega naught, so 1 decade below omega naught, the phase is minus 5.7 degrees. And for omega equal to 10 times omega naught, the phase is minus 84 degrees. Also, it is very important to recognize that the phase tends to minus 90 degrees only as omega tends to infinity. Alright, here this is omega much greater than omega 0 is actually only as omega tends to infinity can A be written as this, and therefore the phase is minus 90 degrees. Another way of saying this is the phase of this is tan inverse omega by omega naught, and tan inverse omega by omega naught actually becomes 90 degrees only when omega tends to infinity. For any value less than infinity, tan inverse omega naught may be close to 90, but it is never exactly 90 degrees. This is important, as we'll see in a minute. Okay, so here is the Bode phase plot, the approximate phase plot. So in approximation, if we plot phase as a function of frequency, so we say at omega naught, the phase is minus 45 degrees. At a frequency 10 times smaller, we say approximately the phase is 0. At a frequency 10 times larger, we say approximately the phase is minus 90 degrees. So this is a approximate phase plot of the transfer function with a single pole. Alright, let us look at a two-pole transfer function. So there will be two poles in the denominator. Now here the important thing to realize is that each pole contributes 90 degrees at frequencies much greater than the pole frequencies. So as omega tends to infinity, the phase of this total transfer function will be minus 180 degrees. But this minus 180 degrees is reached only as omega tends to infinity. Therefore, for any finite omega, any omega less than infinity, the phase is always greater in magnitude less than 180 degrees. Alright, so it may be 178, 179 degrees. It will never become 180 degrees because that happens only as at an infinite frequency. Therefore, okay, so for oscillations to occur, what we want is that at some finite frequency omega naught, the phase becomes exactly minus 180 degrees. But for a two-pole transfer function, this condition is never satisfied because at no finite frequency is a phase exactly minus 180 degrees. Alright, so therefore, two-pole transfer functions never become unstable, never reach that condition of a j omega 0 equal to -1. Such systems are called as unconditionally stable systems. All right. In other words, to say this in other words is to say that the phase margin of a two-pole system is always positive. The phase margin never becomes 0. Of course, this automatically implies that single pole transfer functions are also always stable, right? If single pole will at the most get a phase of -90 degrees. Therefore, one pole and two pole transfer function systems are always stable. They never become unstable. All right. Let us look at a three pole transfer function. Now, so I have put numbers here and I have designed the numbers and the gain such that this transfer function satisfies the condition a j f0 equal to -1. All right, I'm just replacing omega with f because there is the 2 without 2 pi. It's easier to work with these numbers. So all right, so let us look at the Bode plot of this. You can plot this because this requires exact plotting. Let us do some mathematics and Bode plot of this. Okay, so here is the transfer function. So at very low frequencies so for f much less than 10 raised to 7, these three denominator terms are all equal to 1 and the gain is 123, which is about 42 dB. Okay, so I'm plotting this as on the x-axis is f divided by 10 raised to 7, or this is 1 times 10 raised to 7, this is 10 times 10 raised to 7, and so on. All right, so up to 0.1 times 10 raised to 7, we say the phase is flat. Up to 10 raised to 7, the gain is flat. At 10 raised to 7, when the first pole is encountered, the gain starts falling at -20 dB per decade. At 10 raised to 8, the second pole is encountered. So after 10 raised to 8, the gain starts falling at -40 dB per decade. It turns out that at 33 times 10 raised to 7, the gain becomes 1. Approximately, that's little less than 33. At that point, if you evaluate the phase, it is -180 degrees. All right, so at the unity gain frequency, or when the gain is 1, the phase is -180 degrees. So this has a equal to -1 at omega equal to, or f not equal to 33 times 10 raised to 7, and this system has a phase margin of 0. All right. Let us go through the mathematics of this. This is interesting, and this is not done. I have never seen this done, so I am doing this to get a feel for the numbers. Okay. So what of course this means is that because this satisfies the a equal to -1 at some frequency condition, under unity gain feedback, it will exhibit oscillations. So let us find the closed loop transfer function and look at the transient response just to confirm mathematically this condition. Alright, so you say a over 1 plus a, where a is this, and then we take this whole denominator down, plus 123 that comes from here, and then we expand this out as a cubic, and the cubic becomes this, where this 123 is staying. And then if we find, so this is a cubic polynomial, so we find the roots of the cubic, and there are lots of websites which will give you the roots of polynomials. So these are the roots. So there is one real root and two complex conjugate roots, and so we can write the transfer function as s plus 1.11 10 raised to 9 into s squared plus the square of this. Alright, so that is 1.11 times 10 raised to 17. So this is of the form s plus a and s squared plus omega squared. Now if we apply a step function to the input and find the transient, so the closed loop is this a1 divided by s plus a s squared plus omega squared into the unit step, which is 1 by s, and then we want to find the transient in time domain, so we do partial fractions. So the partial fractions of this, if you recall, are some constant a1 goes out, and we'll get an s plus a term, we'll get an s squared plus omega squared term and another s term. And so the numerator for this s squared plus omega squared will be some constant s plus another constant. And now we take the inverse Laplace transform. The first term gives an exponential e raised to minus at. The second term gives a cos and a sine, cos omega t plus sine omega t. I should have made this omega naught, I'm sorry, but this is omega naught, which has a specific value. So omega naught, and then C4. So clearly, as a function of time, the e raised to minus at will die out after some time, but the output will show sustained oscillations, all right, due to the cos and the sine terms. Sustained because these are not damped by an exponential, all right. So this mathematics confirms what we saw qualitatively, that when a is equal to minus 1 at some frequency omega naught, we will see oscillations. So this mathematics shows that. Another way of looking at it, as you know, is that this polynomial, closed loop polynomial, has two poles on the j omega axis, and when you have poles on the j omega axis, the system shows oscillations. All right. Now let us increase. So the gain was 123.21. Let us increase the gain slightly to 124, all right, and see what happens. So we'll first look at the Bode plot and then again do the same mathematics of step response and inverse Laplace transforms. So this is qualitative. So this was this lighter line was for the earlier gain of 123. The darker line is the gain has increased a little. This is of course exaggerated on a dB scale, but this is just to illustrate. So when we increase the gain, basically the whole magnitude Bode plot shifts up. The phase plot is not affected. All right, the phase plot here, where is it? This one. The phase behavior is independent of the gain, all right. The gain does not do anything to the phase plot. So here we are changing the magnitude of the gain, so the magnitude Bode plot shifts up, phase plot stays the same. Now if the magnitude plot shifts up at the first pole frequency, the magnitude is higher. At the second pole frequency, the magnitude is higher. Therefore, the frequency at which the gain becomes unity is now slightly higher, all right, than it was with the gain slightly lesser. Frequency at which the gain becomes 1 is higher. The phase plot is the same. Therefore, the phase, when the gain becomes unity, when the gain becomes unity, the phase is more negative than minus 180 degrees. All right, it was minus 180 degrees for the lower gain. For the higher gain, the phase is slightly more negative. In terms of phase margin, we'll say that for this higher gain, the phase margin is negative. All right, because the phase is maybe minus 183 or minus 185 degrees, so the phase margin is negative. All right, let us look at the actual equations. So now the gain is 124 instead of 123.21. So this number changes, everything else remains the same. If we find the roots of this cubic polynomial, we'll get minus 1.11 10 raised to 9, and the complex conjugate roots now have a real part. In the earlier case, it had only an imaginary part. Now it also has a real part. The numbers have also changed, but for our discussion, the numbers are not of great significance. What is significant is that there is a real part, and that real part is positive, right? The real part is positive. So if we were to factorize this and write the factors, then we'll write s plus 1.11 10 raised to 9, and these two will be s minus, because this is plus, we'll get s minus 2.9 10 raised to 5 the whole squared plus this whole squared, right? So this is the transfer function for the slightly larger gain. Now let us find the inverse Laplace transform. So this is of the form s plus a into s minus b the whole squared plus omega squared. And then if you apply a unit step, it is 1 by s. And then we do the partial fractions. The partial fractions can be written in this form: something by s plus a, something of this type divided by s minus b the whole squared plus omega squared plus something by s. If we take the inverse Laplace transform of this, the first term will give e raised to minus at as before. The second term, because of this s minus b, will give an e raised to bt into cos omega plus sin omega plus c4. This is e raised to plus bt because this is s minus b. Why is this s minus b? Because this is a positive real part. Why is this positive? This is directly related to the phase margin being negative. Alright, there is a direct correlation between the phase margin being negative and this root having a positive real part. What happens therefore in the transient response? If a unit step is applied, then the output shows a sinusoidal whose amplitude is rising exponentially with time. Right? This is positive feedback. This we had seen in the last lecture also. So when the phase margin is negative, a negative feedback system exhibits positive feedback at high frequencies. At this frequency, this positive feedback is only at omega naught. Right? And because of this, the output of the closed loop system rises exponentially. It's a sinusoid that rises exponentially with time, and therefore the system will show sustained oscillations whose magnitude is limited by the nonlinearity of the circuit. So we had seen last time that the exponential magnitude of a circuit is limited ultimately when transistors go into triode or turn off. In a system where sinusoidal oscillations are occurring, the sinusoidal oscillations will continue, but their amplitude will be limited by the nonlinearity of the circuit. So this is the consequence of a negative phase margin. All right, and this is why, of course, to make a system stable, we must keep the phase margin positive. All right, to build stable amplifiers, we have to make sure that the phase margin is positive. Okay, so I did not discuss this, but you can try this yourself. If the phase margin is positive, so what you can do is, here we did increase the gain to 124. Suppose you were to reduce the gain, alright, from 123 to 120 or something, then the magnitude plot will go down, the unity gain frequency will be lower, the phase will be magnitude will be less than 180 degrees, so minus 175 or whatever. Phase margin will be positive, and if you go through, and it will be good if you go through the mathematics of it, you will find that the roots, the complex roots of this polynomial have a negative real part. Alright, that negative means this is positive, and if this is positive, then this exponential is negative. All right, and the sinusoidal will die out as a function of time, and the output will not be unstable. It will be stable, but it will be underdamped, so that the output will show sinusoidal oscillations that will die out as a function of time, which is of course a property of underdamped systems. Now this will happen if the phase margin is positive, but the phase margin is small. As the phase margin becomes larger, all right, the magnitude or the amplitude of the sinusoidal oscillations will reduce. The underdampedness of the system will reduce. And as the phase margin becomes greater and greater, at 45 degrees phase margin, the underdamped oscillations are about, I don't remember, a small fraction of the amplitude of the output. If the phase margin becomes 60 degrees, then these poles they stop being complex conjugates, they become real. The system becomes overdamped, and one does not see any ringing or sinusoidal oscillations in the step response of the system. All right, therefore, to build stable amplifier systems, it is always desirable that phase margins are greater than 45 degrees. Even better, greater than 60 degrees, because at 60 degrees there is no ringing at all. Phase margins positive but close to zero are not desirable. Although the amplifiers are stable, first of all they show significant ringing, but the other is that let us say you design an amplifier with a phase margin of 5 degrees. Now what will happen is every process, temperature, everything will vary, and as everything varies, because of the variation, gain, GAMs, this, that and the other, the phase margin may go negative. And if it goes negative, suddenly the amplifier become unstable. So to ensure that the amplifier stays stable against process voltage temperature variations, also one makes the phase margin significantly larger than 0 degrees. 45 is absolutely minimum, 60 is what is recommended. All right. Okay, so now let us think about, let us relate the phase margin to the Bode plot. So we'll for this lecture and the next lecture we'll work with a phase margin of achieving a phase margin of 45 degrees. So let us see what should the Bode plot look like to achieve a phase margin of 45 degrees. Now a phase margin of 45 degrees implies that the phase of the transfer function at unity gain frequencies minus 135 degrees, right? Because phase margin is 180 degrees, and if the phase is minus 135, we'll get a 45 degrees phase margin. So what we want is that for our amplifier to be stable, and for it to have a phase margin of 45 degrees, the amplifier open loop gain must have a phase of minus 135 degrees at the unity gain frequency. Okay. Now we recall that at a frequency much greater than the pole frequency, one pole causes a phase shift of minus 90 degrees. All right. At the pole frequency, a pole causes a phase shift of minus 45 degrees. And 90 plus 45 is 135 degrees, right? What this therefore means is that in our stable open loop gain of an amplifier, we can afford to have one pole before the unity gain frequency and one pole at the unity gain frequency. One pole before and one pole at the unity gain frequency will give us a phase of minus 135 degrees and therefore a phase margin of 45 degrees. Okay, I repeat because this is very, very important. or let's look at it from the Bode plot. So in this Bode plot, at low frequencies, the gain is flat, the phase is 0 degrees. When the first pole is encountered, the gain starts falling. The phase at that pole frequency is minus 45 degrees. And then the gain keeps falling and falling and falling. When the second pole is encountered, at that pole, the phase, okay, so this, well, the way I have drawn it, this is continuous, but it doesn't need to be. So this pole causes a minus 90 degree phase shift at frequencies much higher than P1, and then P2 starts contributing phase at a frequency about 10 times before P2, and at P2 the phase has reached minus 135 degrees. If we want a 45 degree phase margin, P2 must be at the unity gain frequency. Alright, and then we'll get exactly a phase margin of plus 45 degrees. So this is what we will want to design a stable amplifier. Alright, okay. So about high gain. So let's think about high gain amplifiers. Now we've looked at high gain amplifier configurations. We know that high gain amplifiers require at least 2 stages of amplification. So either we have the 2-stage op amp, or we have the cascode, the telescopic or the folded. Cascode is basically 2 stages, effectively a common source followed by a common gate. So you need at least 2 stages of amplification. Now each stage introduces 1 or 2 poles in the transfer function, and therefore high gain amplifiers always have at least 3 or more poles. We have seen this in our discussion of the various amplifier configurations. So they'll have at least 3, typically 4 poles in their transfer functions. Now because high gain amplifiers have a high gain, it will turn out that 2 or 3 of its poles will be above the unity gain frequency, because the gain is high. It starts out high, and then by the time it reaches unity gain, it would have encountered 2 or 3 poles. All right. What we want is only 1 pole above the unity gain frequency and another pole at the unity gain frequency. High gain amplifier, so maybe I'll go back here to this one. Which one? Not even this one. Yeah, this one. High gain amplifiers will have at least 2 poles above the unity gain frequency. And see, this is not even a very high gain. You're talking about 10,000 and 50,000. This gain plot goes up. The frequencies will stay above. So at least 2, maybe even 3 poles above the unity gain frequency, which will make the amplifier unstable, because all we can afford is 1 pole above the unity gain frequency. Therefore, high gain amplifiers by their own construction are almost always unstable, all right, as they are designed. Right, when we design, so all the amplifiers configurations we have looked at that were high gain, the GMRO, the whole square type of configurations, they will almost always have 2 poles above the unity gain frequency, therefore a phase margin either 0 or less, and therefore unstable. What this means is that we'll have to do something to these amplifiers to make them stable, and that process is called frequency compensation, which we'll see in the next lecture.